Okay, so till now we have completed uh, the basic definitions. So first we will see a small introduction about HVAC, and we have went through the heat definitions. So after that we went to psychrometric calculation, and still some people have to submit the assignment. Please submit it. So that is a basic thing. So whenever you do something, so that will be useful for you. Like practice should be must and should. So try to make the assignment. And next one is refrigeration cycle. So our all air conditioning equipment will work under this refrigeration cycle. Okay. So next one is AC equipments. So we, based on the application and based on the different types of buildings and requirement, so the air conditioning equipments will be differently taken into consideration. So next one is heat load. So till here we have seen the definition, psychrometric chart, and refrigeration cycle. So the main topic in HVAC is the heat load topic. Okay, so in this heat load, we are going to learn the, if we have one building or one room, so if we want to do the heat load calculation, so what is the tonnage required, what is the CFM required, so that we need to derive. So by doing the heat load calculation, we will get to know the how much tonnage and CFM is required. Okay, so the most important topic. So in this heat load also we have Excel sheet. So in Excel sheet we can do it in 5 minutes. Okay, but if we learn it in Excel at the initial stage, so the formulas, everything you will not be remembered. So why I am trying to teach you in manual method first. So in this manual method, so we have the calculation sheet. So the calculation sheet will looks like this. I will share. Can you able to see my screen?
Yes, sir.
Yeah, okay. So this is our manual calculation sheet. Okay. So by this sheet we will do each and every calculation manually. Okay. So after this we will go to the Excel sheet. So then only you will be know the how what are the formulas we are using in this heat load sheet. Okay. So first we'll learn manually, and we will also learn the Excel sheet. So whenever you are in industry, obviously you will use Excel sheet or the software. But if you know the manual calculation, so the each and every formula you will be memorized. Okay. So everybody has to practice this. So after this calculation, today only I will share the assignment for this. So whatever I am doing in everyday class, so you need to do it at the separate, like take the assignment and do it. Okay. So here this heat load will take up to 4 days. So we'll continue that. So daily, whatever the part we completed, so you need to do the assignment also. Okay. So first I'll open this. So first we'll see what are the things we need to take into consideration while we are doing heat load calculation. Okay. First is the introduction. The purpose of cooling or heating load calculation is to provide comfort condition in space which is based on climate conditions. So what is the purpose of giving cooling or heating calculation? Because of comfort condition inside a space. So whatever the climate may be, it is a monsoon, winter, or summer. So we required a comfort condition. So we know that the human comfort temperature is 25 degrees centigrade and 50% relative humidity, right? That we have discussed in introduction class. So for this, we will calculate heat load calculation. So in summer season, heat gain is calculated so that cooling is provided by removing heat. So in summer, usually the temperatures will be very high. It is around 40 degrees, 45 degrees, 35. So depending upon the locations, the temperatures will be way. So in that climate condition, we required a cooling. So to lower the temperature from, for example, if it is 40 degrees centigrade, so we'll convert that to 25 degrees centigrade. So next one is in winter season, heat loss is calculated. So that heating is provided by adding heat. So in winter season, so depending upon the climate locations, so if you take the Indian locations, so that will be around 15 degrees somewhere, 12 degrees also somewhere. So there, what we have to do heating. So to raise the temperature. So 12 degrees or 15 degrees is not the human comfort temperature. So we will raise up to the 25 degrees centigrade. Here, what is required in winter season, that is heating. In summer, required cooling. But in winter, we have to do the heating to raise the temperature. Okay. So undoubtedly, one of the primary reason for failures in air conditioning plants is due to improper estimation of heat load and failure to take into account various factors which affect it. So whenever you are doing heat load calculation, thoroughly you need to take the all consideration. So if you see some of the major failures in air conditioning plants due to the improper heat load estimation. Okay. So if you have not estimated the heat load properly, then your air conditioning equipment will be a failure. Okay. So this is the most important thing that you need to keep it in mind. So next one, it is not possible to measure this actual instantaneous peak load, but only can be estimated. Before estimating this load, a complete survey of the building, if the building exists, or the plans in case of new building has to be done. So heat load is not the perfect estimation. Uh, we cannot estimate it properly because it has major effects. So, for example, if you have designed a building, so if you designed a office space uh, for the 20 people, okay, and the heat load also you have considered like uh, 10 kilowatt or 5 kilowatt, okay, electrical equipment, nothing but our laptops, printers, everything. So you have designed for the 20 people and the 10 kilowatt equipment load. So after that, there might be an increase of the load. So 20 people might become 25 or 30 also. So in that consideration, so this heat load, this air conditioning equipment will not work properly. So that is a major thing. So but we can estimate it. So before we are doing calculation, so we need to take some safety factor and what are the major effects will be going to happen, that we need to consider it and we need to do the calculation. Okay, always we need to take the higher values and also the safety factors. So some following data, the following data need to be collected. So whenever we are doing heat load calculation, the data should be mandatory to collect. So first one is orientation of building and latitude. So the building is uh, orientation is important, like north, northwest, south. So what are the direction of the building? The four sides we need to take, and also the latitude. Okay. And the second one is application. So application is nothing but the building is used for the office space or like theaters. So like this application we need to find out. Next, third one is the dimensions of the building. So each and every room, whatever you are doing the heat load calculation, that dimensions you need to take it. So if it is a high-rise building, so always you will get the architectural drawings. So otherwise you need to, if you're doing for small projects, so you need to find out. So if it is already constructed project, so then you don't have any CAD drawings available. So you need to find out the dimensions and height up to ceiling. What is the height from floor level to true ceiling. The next one is height up to false ceiling. So what is the false ceiling height? Okay, and is the roof exposed? So whatever the building or room you are designing, whether the roof is exposed to sunlight or it is covered with anything like it is covered with other floor, or whether it is shaded. Shaded nothing but it is covered with like any construction on top of the floor so that it is not directly exposing to sunlight. So these you need to consider. And next one is size and number of windows. So okay, for example, you are taken one room. So what number of windows you need to take? So for that room, if we have two windows, so that number of windows we need to take, and size of the window also we need to take. So next one is whether windows are shaded. So whether the windows is shaded or it is directly exposing to sunlight. So shaded nothing but we'll use blinds to cover the windows, so that if you are using the blinds, so the sunlight will not hit the glass directly. So that we need to take it. Next one is material of construction of walls, ceiling and roof. So the ceiling, wall and roof material is like masonry walls or any other partitions like gypsum partitions, aluminum partitions. So the material we need to take it. So always wall, ceiling, roof will be walls and roof will be of masonry only. Only the ceiling will be of different types. Okay. And next one is outside dry and wet bulb temperature. Okay. So outside dry bulb and wet bulb temperature. So what is the area? What is the location you are designing? For example, it is Delhi, Mumbai. So that that outside temperatures and wet bulb temperatures you need to find out. So that we can get it from the ISRO handbook or ASHRAE handbooks also we can get this data. The next one is inside dry bulb temperature and relative humidity. So inside dry bulb temperature, it is the requirement of the client. So whether it is a normal area or like office spaces or any other malls, etc. So the inside temperatures will be, we know that the human comfort temperature, that is 25 degrees centigrade, and relative humidity also 55 or 60. But in conditions like pharmaceutical industries or food industries, so the temperatures and relative humidity will be vary. So depending upon the product, the food requirement, there might be a low relative humidity or high relative humidities. Okay. So if there is any situation, if the client requires specific humidity, special humidity or temperature, so that we need to take it into consideration and we need to do the calculation. Next one is the number of persons. So how many persons will be working inside the room, that we need to add here. Okay. So depending upon the application. So if it is office area, more people will be there. Okay. So next one is lighting load and type of light. So lights also will emit some heat inside the room. So for this lighting load also we need to take. And depending upon the type of light, the lighting load will be vary. Okay. So that we need to take it. So we are doing MEP totally. So you are going to design the lighting load also. So otherwise you need to take it from the electrical person. So next one is machinery load with diversity. So machinery loads nothing but if it is an office space. So we have 20 laptops or systems we have available there. So that also will emit some heat inside the room. So all electrical equipments will emit some heat. So whenever you are designing a room, so we need to take all the electrical equipment loads. So that will emit some heat. So due to that heat, our air conditioning equipment design will be vary. Okay. So machinery load with diversity. So diversity nothing but if the we have 20 laptops. so that 10 laptops was using for 12 hours and 10 was using after 12 hours. So we need to consider only the quantity 10 numbers, because always there is a higher quantity of 10 numbers, only 20 numbers is not using at one time. So there is a diversity. The next one is ventilation required. The pressure requirement inside the room we need to consider. So depending upon the requirement, so the ventilation air will be varied. So ventilation we are going to calculate this. The next one, details of exhaust, if any. So if there is any exhaust from the room, that we need to take it here. Okay, so the objective of this heat load is to calculate the heat load inside the space in BTU per hour and TR cooling capacity. Okay, so the main objective of this heat load calculation is to derive the tonnage inside the room. So we already discussed that when we do the heat load calculation, we will get two values. So one will be of tonnage, okay, TR. So we can also take it in BTU per hour. So 1 TR equals to 12,000 BTU per hour. Okay, so tonnage we will get, and also we will get CFM to calculate volume of air in CFM, cubic feet per minute. Okay, so these two we will get it by doing heat load calculation. Next one is solar gain. Heat gain due to absorbed solar energy from sun rays. Intensity of sunrise 440 to 415 BTU per square feet per hour. Okay, so we will calculate the heat gain from the sun, like through windows, doors, roof, walls, and any other partitions. So all solar gains we will calculate from the for the room. Okay. So next one is transmission gain. Heat gained from unconditioned space. So whether if the space if the room we are designing, so that is connected with unconditioned space. Unconditioned space nothing but non-air conditioned area. So if our room is connected with unconditioned space, so there will be a transfer of heat from the other room to this room. So we need to consider this unconditioned space load also. Okay. So next one is infiltration. Leakage of air inside the space through cracks, opening doors, etc. So when we are opening the door frequently, so some amount of air will be infiltrate from outside to inside. So that is called infiltration. So it might be goes with minor cracks and windows leakages also. The air will be leaked. Next one, effective room total heat. So sum of all sensible heat load we will get effective room total heat. Effective room sensible heat and latent heat. When we sum both, we will get total heat. Next one, effective sensible heat factor. Ratio of effective room sensible heat and effective room total heat. So we'll get the heat factor. So these terms we don't need to worry, from transmission gain to U value. So all these we are going to derive in this heat load calculation. Okay. So next one is U value, defined as overall heat transfer coefficient in depending upon material resistance. So this U value also we are going to find out. Okay. So this is our heat load calculation sheet. So this I have taken from ISRA handbook. So we'll do it first manually, and we'll go for the next Excel format, and after that we'll go to for the HAP software, hourly analysis program. So this is a sample project. So project location is New Delhi. So this is our example project. We are going to calculate the heat load. Okay. So project location is New Delhi, and weight of the wall. So wall weight and weight of the roof. So this is the details we need to cover. We need to take it from the client or architect before we are doing the heat load calculation. So first project location is New Delhi and weight of the wall, weight of the roof. So this we will get it from the architect. So weight of the wall is 60 lb per square feet and weight of roof is 80 lb per square feet. So exterior wall type. So this is we can know that by using the architect file we can uh, take this value like exterior wall type thickness and partition wall type thickness. So I will show the image here. So this is the architect layout here. So we have the office space here. So we are going to design the heat load calculation for this office space that is of 150 square feet. Okay. So this 150 square feet office space exterior wall type is 9-inch brick masonry. So if you see this is the exterior walls. So these all are the exterior walls that is of 9-inch masonry construction. And partition wall type 4-inch solid block. So this is the partition wall. So partition wall is nothing but which is not directly exposing to sun. So this outer part is directly exposing to sun. So this internal part is connected with another room. So the directly it is not exposing to sunlight. So we call this as a partition, which is separated the from other room also. And next one is roof type. So this roof, if we consider the roof is exposing to sunlight, so this is the thickness of the roof, 6-inch thickness RC slab with waterproofing also. And floor type. So this is a floor type. So that is a detailed 6-inch concrete floor and 6-inch RCC partition. So this in all conditions, this data will be of same. So depending upon some constructions, exterior wall type and interior will be varied. So roof and floor almost it will be same. And this also you can take it as the same value. So okay. Okay, so today we have seen just introduction about this. So from tomorrow onwards, we will calculate the heat. Okay, this is our manual heat load calculation sheet. So which we have seen in our last class. Okay, so after this class, I will share this. So you can take this printout and whatever we are completing day by day. So you just practice this uh, heat load sheet. So I will share the assignment today. So I will work on one example so that you can work on this assignment. So simultaneously, whatever I am doing on the heat load calculation, with the help of this assignment, you can work on this heat load sheet. Okay. So here to enter the values, I have just uploaded it to AutoCAD. So now required, you can take out the printout and you can easily practice it. Okay. So fine. So this is our heat load calculation sheet. So first we need to enter some data here. So this is the job name, address, and space used for. So job name. So for this we need to take one example. So that we have already seen in our last class. So I will open that. So this we have seen the introduction and objective. So this we all discussed. So here we have one example. So this is the architecture layout. Okay. So in this architecture layout, we are going to calculate the heat load for this office space. So this is the office space. Okay. So we need to collect this data and we need to calculate in our manual sheet. So first I will write it job name. So job name, you can write it as heat load calculation or something. So we can also write it as a client name. Okay. And here the address should be there. So the client address. Okay. And next one is space used for. So we are designing this for the office space. Okay. Next, the size of the building. So the office space size. For this, we need to go to PPT. So width of the building is 15 feet. So the dimensions was mentioned in feet. So you can see the width of the building is 15 feet here and the length is 10 feet. Okay, so that is the room dimension. So I will write it here in 15. So remember that all the values taken here in heat load calculation is that is in feet or square feet. Okay, 15, 10. So what will be the square feet here? 15 multiplied by 10, 150 square feet. So next here we need to enter the height of the building. So again we'll go to drawing. So here we don't have height in this drawing. So let us assume some height. So generally our false ceilings will be at the height of 9 feet. Okay. So in this drawing we here it was not mentioned, so that we will assume that height is a 9 feet. So in real time we need to confirm with the client whether they are going with 9 feet height or they are increasing some false ceiling height. We need to confirm. So 9 feet I will. So when I multiply this, how much I will get? 150 multiplied by 9. So that is 1350 cubic feet. Okay, fine. So next we'll complete this indoor and outdoor conditions, and next we'll go to other parts. Okay, so first here we need to enter the conditions of the outdoor environment and indoor room environment. Okay, so we are designing this project on which location we will see. We are designing the project in New Delhi location. Okay, so we need to enter the New Delhi outdoor conditions. So for this we need to refer the ISRE handbook. So I am referring the ISRO handbook, but also in ASHRAE also same data will be available, and in career handbook also same data is available. So career handbook I already uploaded in the drive. So in the material folder you can see the uh, career handbook. So all these details also available in career handbook. Okay. So go through this. So for here for my convenient I am using this ISRE handbook. So these all are the pages which I was separated from the ISRE handbook. So don't get confused. Only this is the ISRE handbook. So all these I have segregated for easy pick up in the data. Okay. So here, what is the requirement outdoor design data? So I'll open this outside design data page. So this is a table 1, outside design data. So here we have the state and stations. So first we will see the state. Which state it is? New Delhi. So UP and Delhi. So here you can see this is the New Delhi values here. Okay. So what we required here, that is dry bulb temperature, wet bulb, RH, DP means dew point temperature, and humidity ratio. So learn this short forms. DB means dry bulb, WB means wet bulb, RH means relative humidity, DP means dew point temperature, grains per LB means humidity ratio. Okay, so remember this all full forms. Okay, so this is nothing but same what we have done in psychrometric calculation. So the same thing we need to do it here. So for this we require two values, right? For the two values we are going to we are going and taking in the ISRE handbook. Okay, so for New Delhi, so these are all the values. So we'll go top and see. First is latitude, where it is located, and altitude in meters. So how much height it is from base. So daily range. So it is sum of average heat in the entire year. Okay. So summer conditions, dry bulb, wet bulb, and RH. Monsoon, winter. So it is in Fahrenheit. So same thing, summer, monsoon, and winter. That is in degree centigrade. Okay. So we are taking the values in Fahrenheit. So I will consider this as a summer season. So I will design for the summer. So I need to take the value of dry bulb, wet bulb, and relative humidity. So three values is available. So this is the New Delhi. So dry bulb value is 110. I will enter here. So what is the wet bulb value? Wet bulb value is 75. And RH value is 20%. Yes, RH is 20%. Okay. So we need to find out the rest of the values from the psychrometric calculation. Okay. So we leave like this. So next we need to enter the room conditions. So room conditions. So in our first class, what we have discussed, the human comfort temperature. So I'll open that. So if you see here, temperature, the human comfort temperature is 24 degrees centigrade. So what is required in office space? So only the human comfort temperature. So that way I can take it as 24 degree centigrade. And moisture in the air, humidity also it is mentioned 50 to 60% is a human comfort humidity. So we'll take the same. So I'll write these are the room conditions. Okay. So I'll write it as 50 here, relative humidity. Okay. So I will convert 24 degrees to Fahrenheit. So what is the Celsius? That is 24. So Fahrenheit we are getting 75.2. So I will take it as a 75. 75. So if we know the two values, so we can find out the rest of the value. So first we'll find out the outside design values, and next we'll derive the room conditions. Okay. Okay, so this is our psychrometric chart. So we have seen how to calculate the psychrometric and derive the values in our last classes. So again, we'll see this. So if you go to our calculation sheet, so outside dry bulb is 110 degrees centigrade. Sorry, 110 degree Fahrenheit. So I will mark a line at 110. So this is the 110 dry bulb line. Okay. So next one is any one value we can take. So we have two values, that is wet bulb and RH. So I will take one value, that is wet bulb 75. So wet bulb 75 line. So this is a wet bulb lines 85, 80, and this is a 75. So I'll draw one line here. Fine. So here we will get the rest of all the values. Okay. So whatever the values required, we will see it once. So that is dew point temperature and humidity ratio. So where it is dew point temperature line. So this is a dew point temperature scale, and this is a humidity ratio scale. So when we draw this one line, so we'll get these two values. Okay. Okay. So what is the dew point temperature here? That is 55, 56, 57, 58, 59. So I will enter the same here. Dew point is 59. Okay, next is humidity ratio. This is the humidity ratio line. So it is in between 72 and 80. So I will take it as 75. Okay, so we have done the outside in the outside condition. So we need to derive inside conditions. So inside condition is room 75 dry bulb and 50% RH. So I will copy one more psychrometric. Room dry bulb is 75. So I will draw one line. This is the 75 dry bulb line. Okay. And what is the RH here? RH is 50%. So where is the RH 50% line? Here, that is. Okay. So I'll mark it here. Okay. So this is the curve of the 50% RH. So, okay, and here from here we need to take the values. So I will draw one horizontal line. So that's why we can get the humidity ratio and differential, sorry, dew point temperature. So what is the humidity ratio here? So it is in between 60 to 70, that is 65. So that is 65 here. So dew point temperature is 55. Okay. So next we required wet bulb temperature. So you can go there. So these are the wet bulb lines: 85, 80, 75, 70, 65, and this is 60. If we draw one straight line, yes. So what will be 61, 62, or 63? So I will take 63 here. Okay, so we have entered all the values from the psychrometric chart. So next we need to take the difference of dry bulb temperature and the humidity ratio. So what is the difference here? 75 minus 110, 85, 95. Right. So 110 minus 75, get 35 here. So next is 60 difference of humidity ratio. So 65 minus 75, that is 10. Okay. So we can also check these values from our carrier carrier psychrometric chart. So that we have already seen in last class. So if you want to calculate in manually method, so you can use this, or else you can use this psychrometric chart for calculation at point. So what is the dry bulb here? So we'll check this whether what we have the values we have taken, that is okay, correct or not. We'll check. We'll also check. Outside design data is dry bulb 110 and wet bulb 75. So dry bulb is 110 and wet bulb is 75. So what is the RH? 19.3. It is 20. Fine. And humidity ratio. No, this is dew point temperature is 58.94. So it is 55. Sorry, 59. Fine. And humidity ratio, it is 74.7. Is 75. That's fine. Next, we'll check the room conditions. That is 75 dry bulb and 50% orange. 75 and 50. So this is orange. Okay. So what is the wet bulb? 62.5. So 63. Fine. Next is dp, and dew point temperature is 55. That is 55, correct. And humidity ratio is 65. Humidity ratio is 65, 64.9. So right, we have taken the values correctly, so we can proceed. So if you don't want to do this manual calculation, you can simply use this software. Okay, fine. So there is a difference also we got here. So next we'll go for the calculation of solar gain through glass. Okay, so solar gain to glass formula is, I will write it here. Q equal to U multiplied by A into delta T. Okay, so this is a formula for calculating the solar gain through glass. So U is the value, heat transfer coefficient, and A is the area of the glass, and delta T is the temperature difference. Okay, so this is the formula for solar gain through glass, and for the solar and transmission gain through walls and roof also same formula, and transmission gains except walls and roof same formula. So till here the formula will be same. Okay, so first solar gain through glass, we need to take the U value. So we will enter the U value here, and square feet here, and the temperature, no, square feet here, delta T here, and U value here. So first I will write the square feet of the glass. So how we need to take the square feet of the glass? So for this we need to go for our drawing. So if you see, we are designing the for this office area of this space. Okay, 15 by 10 feet, 150 square feet area. So we need to check whenever we are doing calculation, so whether we have the windows that is there for this room that is exposing to sunlight or not. So if you see, we have two windows here, so that is exposing to sunlight. So this is outdoor environment. So when this windows is here, when the windows is here, so it is not required to take the value. So but here the windows is here and it is exposing to sunlight, so we need to take the value. So, and also the direction we need to see. So this is the north direction, right? So this is the N that is showing this is the north, and this will be the south, and this will be the west, and this will be the east. Okay, so we will write direction first here. So the glass direction. So in our example, we have the glass in south and we have the glass in west. Okay, so don't get confused. If you're not understanding anything, so you can stop me and you can ask me. Okay, so south we have the glass and west we have the glass. So I will write heat here first. I'll write it as south here, south and west. So if you have more glasses in different directions, so you can enter. So only we have two in this example, so I am assuming these two. So if you have, for example, if you have in north side or in east side, so you can take how many windows is available. So based on that we need to take. Okay, so I have taken the north and south, and I need to enter the area of the windows. So window one, how much that is? window 1 is on west side, so that is 5 by 4 feet. 5 feet by 4 feet. So when we multiply this, 5 of the 20 square feet. So that is on west side. West side, that is square feet is 20. What is the south side square meter? So south side is W2. So 7 multiplied by 5, that is 35. Okay, so next we have entered the area here in this formula. So next we need to enter the delta T. Okay, so for this delta T we need to go for the history handbook. Okay, so what we required here, so we required square delta T. So I will close this. So I have opened the glass temperature difference for the ordinary glass. So for temperature difference, if you see this table, so here we have 10 degrees, or 20 degrees and 30 degrees was mentioned. That is in latitude direction. Okay. So based on our project location, if it is Delhi, one latitude will be there. If it is in Hyderabad or if it is in other countries, Dubai, somewhere. So it will change based on the location of the project. Okay. So what is our project location, that is New Delhi. So if you go to this chart, that is outside design data chart. So we have the state and station, next one latitude. So we are designing for the New Delhi. So what is the latitude here? 28.35. So what we need to do, so after selecting this 28.35, we'll go to glass temperature difference. So this is 10 degree north latitude. So it is not required. We'll go move on to next one. This is 20. So next one is 30. So our value is 28.35. But we don't have the 28.35 exact value. So we will move on to higher value, or else the nearest value. So that is 30 degree latitude. So if you say take this 32 value, so this is our table to take the delta T values. So here also, if you see, we have so many values, that is June 21st, July, May, August, April, till the entire year we have the different values. So if you remember, we are doing it for the summer condition. So we are doing the calculation for the summer condition. So what we need to do, we need to take the values that is in July to May. So why? Because this is the summer condition months, and also the peak temperature in summer will be in these months. So July and May month. Okay. So we have selected the month, and next one is exposure. Exposure, we are calculating the two exposures. One is on south and one is on west side. Okay. So I'll select first south value. So this is the south value. And if you see south value, we have more number of values here. So that all the time from the morning to evening. So morning 6 a.m. to noon, afternoon, and till the 6 a.m., 6 p.m. in the evening. So as per the data, so the peak temperatures was recorded in the time of 4 p.m. evening. Okay, so what we'll do, we will take the values of the 4 p.m. and we will calculate it. So why I am taking 4 p.m. values means, so as per the records that highest temperatures was recorded in all over the world, that is on at the time of 4 p.m. So always we'll recommend it and we'll do the calculations based on the 4 p.m. calculation. So if you want to do other uh, time calculations also, you can take this. Okay, so as of now I'm taking 4 p.m. values. So this is the south side, and July and May, this is the March month. So south side I am taking the 4 p.m. values. That will be, so what is the value for south glass? That is 12. Guys, call is going to disconnect. So when if the call gets disconnected, please rejoin again. Okay. So this is for the south, and we need to take the another value that is on west side. So it's the same table we can use and same month, but the direction exposure is different. So this is the west side, and same for that is 164. 4 p.m. value. The value is 164. Okay, so what we have left in this formula, if you see, we have entered the area and we have entered the delta T. So we need to enter the value, that is U value. So for this U value, we will go to again for the HVAC handbook U value class. Okay, so this is the table 5. You can see it in HVAC handbook. So this is a type of glass, and we can select the U value from this data. So okay, so for taking the U value, we need to refer this table 5, overall factors for solar heat gain through glass. Okay, so type of glass. So we have ordinary glass, a regular plate glass, heat absorbing glass. So there's nothing but the a slight difference in the glass manufacture. So ordinary glass means, so normal glass when we use, there is no other specified things for that glass. So regular plate, so this is of different type, and heat absorbing glass. Some glasses will absorb the heat, so that will give some advantage to our heat load calculation. So if it is that kind of glass, we need to take these values. And double plane, the single glass are double glasses, and triple plane, triple glasses. Painted glass, so the glass is painted so to absorb some heat, and stained glass. So these are the different types of glasses. So as of now, I will take it as ordinary glass. And if you see here, glass factor no shade. Shade nothing but if your glass is covered with any uh, like curtain or something, so that will not directly hit the sunglasses and will not get the direct heat from outside to inside. So if you are not covered the glass with any of these, so we can take this value. Okay. So another thing, we have inside Venetian blind, outside Venetian blind, outside shading screen, and outside evening. So Venetian blind means, I will show here. So this is called Venetian blinds. Okay. So sometimes we will use the maintain blinds for windows also. So these, if we are using, so we can take these three values. So outside maintain, if we are using inside, we can take this. If we are using outside maintain blind, we can take these two values. So outside shading screen, so outside evening. So these are the different types of windows. So I will take as an ordinary glass and no shade, that is the value 1. Okay. So we need to multiply. We have taken u value, this is u value, and a value, this is an delta t value. So we need to multiply this. So 35 multiplied by 12 by 1. So we'll get the heat in the form of BTU per hour. So 35 multiplied by 12. Get 420. 420 BTU. So next one is west side. So again we need to multiply 20 multiplied by 164. That is 3280. 3280 BTU per hour. So next we can move on to these walls and roofs. So that we will continue from tomorrow. So till here, so if you have any doubts, you can ask me. So and also, so I will give the assignment today. I will upload it in our folder. So same like this. So you have seen this architecture layout, right? So same one PDF I will upload in our this thing in the drive. So you can take the values and you can work on it. Okay. So till here, if anyone has doubts, you can ask me. Okay. Okay. So we have done the solar gain through glass. So then we'll go to solar and transmission gain through walls and roof. Okay. So we'll open the PPT. So if you see the drawing, so we have two walls, which the outer part is exposing to atmosphere. So here, if you see, this is our space, office space. So we have the partition wall. So this wall is separating from the other rooms. So we can call this as a partition wall. So why? Because this is not directly exposing to atmosphere. Only it is separating the room from the other room. So it is separating. So this we call it as a partition wall. And this outer boundary, this is totally the outer boundary. This we call it as a exposed walls. So our room is up to here. So we can take the outer walls from here to here, from here to here. Okay. So the same directions we need to consider here also. This is the north. So this will be the south, and this will be the west, and this will be the east. Okay. So here only the two walls are exposing to atmosphere. So this is the west wall and this is the south wall. So same we need to take it here. So don't get confused when you are practicing. So for example, if this partition wall is not there, so this partition is extended up to here. So in that situation, we need to take this wall also. Why? Because this wall also exposing to atmosphere. So here only, not only it is related to south or west. So whatever the walls exposing to atmosphere, that many walls we need to take it. So for example, if four sides of the wall is exposing to atmosphere for for a one room, so that we need to take four sides of the wall. And also if it is exposing only one side, we need to take one side. Okay, so here in this example we are taking two walls, so it is depending upon the construction. Okay, so in the example what I have given assignment, so in that the three walls are exposing. Okay, so there you need to take three walls for calculation. Okay, fine. So here I will take two walls. So same walls, wall be south and west. So I'll copy this. Next we need to enter the square feet. So this is a square feet of the wall. So for to get the square feet of the wall, so first I will do for the south side. What is the length of the wall here? Here it was already there from here to here, that is 15 feet. 15 into, so we have assumed that false ceiling height is 9 feet. So 15 multiplied by 9. So we'll get 135 square feet. And next west side wall. So west side wall, the length of the wall is 10 feet, and if we multiplied with the height of the wall, that is 9. So that will be 10 multiplied by 9, it is 90. So we'll enter the 90 here. Okay. So next is walls temperature difference. So for walls temperature difference, we need to go for the handbook. So include data. Okay, so this is the table 9 equivalent temperature difference value. So here we can get the wall temperature difference values. So first here we have exposure. So our wall exposure is on first wall is on south. So we'll select the south wall. So northeast, east, southeast, south. So this is the south. And next weight of the wall LB for square feet. So the weight of the wall depends on the construction of the building. So that we can get it from the architecture. So here we have taken weight of the wall is 60 lb per square feet. Okay, so if you don't know exactly, we can take it approximate value of 60 lb per square feet. So or else if we required an exact value, so we can contact the architecture. So okay, so they are the responsible for construction of the building, so they will give the exact value of this weight of the wall and roof. Okay, so here in our situation, that is 60 lb per square feet, so we'll select that 60 lb per south, 60 lb per square feet. So this is the 60 and the south. So these many values we have. So same thing what we have done in glass delta T selection. So here also we are selecting sun time at 4 p.m. So that is the recorded highest recorded values in a summer. So that we will select 4 p.m. So uh, you go and see the time here. So this is the 4 p.m. So 4 p.m. at south, that is 26 here. Okay, so we need to take the value 26. Okay, so after this we need to add some correction factor to this delta t. So we cannot take directly this value. So for adding the correction factor, so we need to go for the next table. So table 11, we have corrections to equivalent temperature difference. So to select this, first is the daily range here. So daily range we need to check from the outside design data. So we'll go to here, outside design data. So we are doing the calculation for the area of New Delhi. So we will go for New Delhi here. So this is the New Delhi. So the daily range here it is 25. So we'll see. So this is the daily range. Okay. Third one. So for New Delhi, the daily range is 25. Okay. So we'll select here 25. So this is the daily range values. So we don't have 25. So we'll go with higher value, that is 26. Okay. So I will select this. And next one here it is outdoor design temperature for month at 3 p.m. minus room temperature difference. So this is nothing but the delta T of the inside temperature minus outside temperature. So that we have already done here, that is 35 degree Fahrenheit. Okay. So this is the delta T outside minus room condition. So we have both the daily range and the delta T. So this is 26 and this is 35, right? 35 and 25. Okay, so this is the 35 value and this is the 26 value. So our daily range is, correction factor is 17. So we need to add this 17 to our delta T. So 26 plus 17, we get 43 here. Okay. So U value later we'll do that. First we'll complete this west side delta T selection. So west side delta T selection, same procedure we need to follow. Okay. So in this table, so this is the table 9. So west side, this is the west side. Weight of the wall is same 60. And at 4 p.m. that is same value 26. Okay. So same we need to select on 26. So they here also we need to add some correction factor. So we'll go to correction factor table. So that is 26 and also this one is 35. We already seen 35 and the daily range is 26. So that is 17. So 26 plus 17, the same value what we have got for the south side, same value we will get it here. So we'll copy this 40. Okay. So for this u value, so actually the u values we need to find out or else we can take it from the carrier data handbook. So in carrier handbook, so it was mentioned clearly. So we can take it from the carrier handbook or else we can calculate in some situations. So if we don't find the u value for the proper material, so we need to find out that u value. Okay. So u value means nothing but heat transfer coefficient. For example, if your wall construction is like 1 inch thickness, so the heat transfer will be high. So if the wall construction is 2 inch thick, so the heat transfer will be less. So depending upon the construction and the thickness of the material and the plasterings, so the u value will be differ. Okay. So here our wall construction is, I will show the one example for the U value calculation. So that same procedure you can follow it for the all type of materials. Okay. So here, our wall thickness is, you can see, 9-inch thickness. That is the outer walls. Okay. So inside walls is 4-inch thickness. So we'll see the outside wall 9-inch thickness example. So after this completion, I will say this part is bypass factor and contact factor. So I'll move this now. So this is the U value calculation. So for U value calculation, so this is the formula R total. R total nothing but resistance. So resistivity R total equal to R still air plus cement plus brick plus cement plus moving air. So this is nothing but it's our 9-inch thickness brick. Okay. So this is a 9-inch thickness wall. So outside we have the still air. Okay. So still air nothing but the, so we'll have some outside air. So the air also have some resistivity. So that resistivity we need to take. So that is 0.68. And next is R cement. This is the cement value. So outside also there will be plastering, right? So that plastering is 1/2 inch. So that resistivity is 0.10. And R brick. So this is the common brick, that is 1.72 resistivity. And again inside we have cement 1/2 inch. So that is 0.10. And inside we also have the air, moving air inside the room. So that value is 0.25. So when we add all these values, we will get 2.85. So U value equal to 1 by R. 1 by 2.85, we will get the U value. So, okay, so we have understand this calculation, but here we need to take the value. So where we need to take this value, 0.68, 0.10, 1.7. So these values we will get it from the data book. So I'll open the data book. Okay, in table 8, you can see thermal resistance are building and insulating materials. So these are resistance of the materials. So here we will get all types of materials. So if you are using asbestos cement board or gypsum board, plywood boards, so every material you will find out here. Okay. So first, what is our material here? We will see in example. First one is moving still air. So this is outside environment air. So still air. So for still air, we will go to another table. Yes, still air you can see here. This we call it as still air. Vertical. So the direction of the air is vertical. The value is 0.68. Okay. So this is the resistance value 0.68 for the outside air. Okay. Position is vertical. So the wall position is vertical. So the heat flow means the heat flow is in horizontal direction. So that nothing but, so the wall is positioned vertical, right? So the heat flow, whenever the sun is emitting some heat, the heat is flowing like this, right? So this we call it as a horizontal flow. So that's why we have selected this value, that is 0.68. So that is the outside air value. So we can keep that as a constant for other calculations also. And next one is cement 1 by 2 inch. Okay. So our cement value. So for cement value, we need to go for insulations, loose fill boards and slab. Yeah, we can see here plastering material. So the cement 1 by 2 inch is a plastering material, right? So here we have, see, in this plastering material, cement, plaster, sand aggregate, sand aggregate. So here we have sand aggregate plastering material. The thickness is 1 by 2 inch. So we can see our cement plastering thickness also 1 by 2 inch. So we can select this value. So that is 0.10. Okay. So this is the value. So we have selected the same value. And next one is R brick value. Okay. So the R brick value. So this is the machinery units, nothing but the constructed material. So here in this we have different types of bricks: brick common, clay brick, concrete block, cinder aggregate, gypsum partition, stone, lightweight. So here we have selected cinder aggregate. So that is of 8-inch thickness brick, and the U value, resistance value is 1.72. So you can see the thickness here also. So that is 8 inches. Okay. So the value is 1.72. So the same value we have taken 1.72, and again inside thickness of this plastering, that is 1 by 2 inch. So we have already seen the value, that is 0.10. So we can select the same value. And next one is moving air. Moving air means inside air. So that we need to find out from the book. Okay, so here you can see the air film, uh, 15 meter per hour wind at any position for winter any direction. So this we are doing for the summer direction, summer season and any direction. So we can select this bottom value, that is 71 by 2 meter per hour wind, any position for summer any direction. So the value will be 0.25. Okay. So we have taken all the resistance values. So when we take all the resistance values and we'll add, so we'll get the R total value. So the R total value is U equal to 1 by R. The formula is 1 by 2.85. We'll get the U value. So the U value here we got is 0.35. Okay. So no need to worry. So these U values you need no need to do on a regular basis. So this for just for your understanding. So when the situation where you don't have the proper U value, so you can calculate by using this method. Okay, so always when you are doing work, so you will take this kind of approximate value and you will do it. And also I think that is available in carrier handbook. So let me check once. So we can see here in carrier handbook, so it was already available. So solid brick, if face and common, common only. So if it is common only, so the thickness of the brick, if it is 8 inch, 12 inch, 16 inch, and if it is none, so it was not plastered or not done anything on that, so we can take these value. So if we have gypsum board on that wall, so we can take these value. So if you have plastering on wall, sand aggregate plastering or lightweight aggregate plastering, we can take these values. So metal lath plastered on furniture, so gypsum, insulating board. So these are the types of material applied on the wall, so that we can take these values. Okay, stone. So in this book, so I have uploaded this book also, so you can check with this. All kind of U values are available in this. Okay, okay, fine. So we have done for the wall side also. So only we'll multiply this, we'll get the BTU per hour. Two 2031. Okay, so next one is roof sun, roof shaded. So we'll go to our drawing. So here, uh, if our building roof is exposing to sun, so we need to take this value. Otherwise, we don't need to take this value. So for example, I will show one example here. Okay, so we have these floors. One is on ground floor, first floor, and second floor. For example, when we are designing the building for the second floor, okay, so on this top of the second floor, we don't have any other floors left. So when the when we are designing for the second floor, so the sunlight will hit directly on this roof. Okay, this part of the roof. So here we need to take the roof sun values. Other than that, we no need to take the values. Okay, so understand this. So it is very important. Okay, so in that situation, we will take the roof value. So in other situations, so first when you are doing first floor calculation, so here the sun is not hitting directly, so sun will hit on the second floor, so it will goes to second floor and it will come to first floor. So if we have air conditioning in second floor, so there will be no air heat transmission from the sun to the first floor. So in this situation, what we have to do, we have to take the partition heat as a partition value. Okay, only whether the second floor area is not air conditioned, then only we need to take the partition value. If second floor is air conditioned, so then we don't need to take the roof value and the partition value. Okay, so again for the same situation, for the floor value, we have the floor, right? So ground floor, if you are doing designing for the ground floor, so we no need to take the floor value. So if you are doing for the first floor, so if this ground floor is not air conditioned, so the heat will be transferred from this room to the first floor area. So that we need to take the floor area. Otherwise, we no need to take this floor area if the ground floor is air conditioned. Okay. So like this, we need to take the value. So here roof sun in this example, I will consider that as a top floor so that I will take the values of the roof. So uh, roof sun and roof shaded we have. So roof shaded nothing but if our roof is covered with any of the sheet or something, so if the sunlight is not directly hitting, we need to take the roof shaded value. Otherwise, we don't have any covers on the roof, so we can take the roof sun value. Okay, so roof sun value here we need to enter the square feet first. So square feet, that is 15 by 10, that is 150 square feet. Okay, I will enter 150 here. Okay, next we need to take the delta T value. So for this we need to go for the data book. So in the table 9, table 10, this is for the roof values. So condition exposed to sun, covered with water or sprayed or shaded. So it is exposed to sun, we will select this value. And weight of the roof that we have mentioned, that is 80 lb for square feet. This is the weight of the roof value. So covered with exposure to sun, this is the 80 value. So same our 4 p.m. value. So if we select, that is 32 here. Okay. So we need to enter the delta T value 32. Okay. So next we need to enter the U value. So we know how to calculate the U value. So we can calculate ourselves. So I have some reference so that every time I don't need to calculate, I will take this value from this book. Roof partition. So this is one reference I have so that I will take the values from this table. Okay. So here we are doing for the roof. So this is the roof or ceiling values, that is flat roof or finished ceiling. So our ceiling, our roof is made up of concrete. So that will be almost 8-inch lightweight concrete deck. Okay, so I will take this value 8-inch lightweight concrete deck value. So that is around 0.08. Okay. Okay, when we multiply this, we will get the value 150, 30. So that is 384 BTU. So next one is our transmission gale except walls and roof. All glasses we need to enter. So all glasses nothing but. So here we have already taken the wall glasses. So that is 35 plus 220. So we need to add these two and we'll take the transmission gain here. So that is 35 plus 20. So that will be 55 square feet. So I'll add these two glasses. I will get 55. And next I need to take the delta t value. So delta t here we need to take it from the out, outside minus inside conditions. Okay, so the difference of the outside minus room, that is 35. Okay, so this delta t we need to take. Okay, so for all glasses we have taken 55 and the delta t is 35. So for partition, so we need to take the partition. Ceiling is not required, so we have taken our example as a second floor. So if we are doing it for the first floor, so we need to take that as ceiling. So here in this the ceiling is not required, so we need to take partition and also the floor value. So floor value we are designing for the second floor. So let us assume that first floor is not air conditioned, so that we also need to take the floor value. So the values here required is partition and floor. So partition value we need to go for our drawing. So this is our partition wall. So you can see this is our partition wall. So this wall is out exposing to outside atmosphere. So we are already taken these values. So the wall which is not exposing to atmosphere and connected with other room, so that we call it as partition. So if for example if this area is not air conditioned, means there is no AC here, so then only we need to take this value. Otherwise that is not required. So let us assume that okay, so let us assume that this is not a partitioned air conditioned area, so that we need to take this partition also. So what is the length of this partition? From here to here, that is 15 feet. From here to here, that is 10 feet. So 15 plus 10, that is 25 feet. So that is the running feet. So we need to multiply with height of the wall. So 25 multiplied by, so 9 feet is our fall ceiling height. So 9, you get 225. Next one is ceiling. So we don't have ceiling in this place. So now we will go to floor value. So floor, how much is the square feet of the floor? So we already know that 15 multiplied by 10, we will get 150 square feet floor. So this is a 150 value. So we need to enter the delta T value. So here delta T values is all glass partition is 35. 35 we have taken from the uh, outside condition minus inside conditions. So for the remaining values like partition and floor, we need to take 35, the difference minus 5 degrees, 5 degrees we need to take. So that is 35 minus 5, we will get 30 and 30 here. Okay, so why I have taken 30 degree Fahrenheit here and 35 here means. So if you see, this is the glass partition. So this is the transmission gain directly from the sun. So when the uh, sun hits the glass, so the sunlight directly enters into our space, our office space. So the light will be somewhere it will projecting inside the room, so that there will be no obstacle for that, so that the temperature will be, the difference will be steady. So that I have taken 35 degree Fahrenheit in the place of partitions and floor. So that's directly the sunlight is not coming inside our room. So if you take here in our example, so this if you take this partition, the sunlight will hit this boundary and it will transfer some heat to this room. Okay, and then it will transfer from this partition to our conditioned space. So these many obstacles we have, so that the temperature difference uh, exactly it will not work out here. So that we have taken some less temperature, that is -5 degree centigrade, 5 degree Fahrenheit. So that is the usual difference we will consider for calculation. So that is for partition, and also the floor also same thing. So we'll go for our example here. So we are doing for second floor. So if the first floor we don't have air condition, so the heat where from where it is coming, this is heat waves coming from these sides of the wall and these sides of the wall. It will enter into this room. It will heat it and it will goes to this floor wise. So this is called the transfer of heat, so that it is not directly hitting the floor, so that we can say that as a uh, less temperature transmission. So that I have taken the 5 degree Fahrenheit less. Okay. Yes. So we have entered the all values, and next we need to enter the u values here. So all glass u value. So we need to go for the u value for glass. This is the u value glass. Okay. So here in table 5, in table 6, you can find out the uh, transmission coefficient u value for the glasses. Okay. So in table 6. So here we have two values, also air space thickness and without storm windows or with storm windows. So I'll show you what is storm windows first. Okay, so these type of windows we call it as a storm windows. So like that we can open it and we can close it from inside or outside. Okay, so this is called storm windows. So we can say that as is office space, so we'll consider that as a without storm windows. Okay, so without storm windows. So we have vertical glasses or horizontal glasses. So the glass, so we'll let us consider that as a vertical glass, and the thickness, single glass is there, or double glass or triple glass, so that these different types we need to take it. So let us consider double glass, and the thickness is 1 by 4 inches, so that our value is 0.61. Okay, so next one is partition value. So for partition we need to go for the different u value. So this is the sheet for partitions. So this is for the walls, partition. So here we can see that we have partition values. So partitions, the partition is masonry. So we have 4-inch cinder block. So thickness of the block is 4 inch. So no insulation, no finish. So we can select this value. Only this value is available here. So we can take the values, that is 0.40. Okay, so next one is floor value. The floor also we can find out in the same sheet. So partitions, walls, roof, ceiling and floor. Okay, so this is the floor value. So here we have two values: floor, tile floor, plywood and concrete deck. So I will take this concrete value. And here also we have heat flow up or heat flow down. From floor means heat is flowing from top to bottom. So heat flow up we need to take. So the summer value is 0.34. So we will take the value as 0.34. So when we multiply these all values, #55 multiplied by 35 multiplied by 0.61 1174. So again 225 multiplied by 30 multiplied by 0.4, 2700. So one is 150 multiplied by 30 multiplied by 0.3, 1530. Okay, so till here we have completed walls, roofs and solar gain through glass. So I think tomorrow we can complete the rest of the sheet. So rest of the sheet is very easy. So we'll try to complete it tomorrow. Okay, still here, if you have any doubts, you can ask me. Till yesterday we have completed up to floor, all glass and partitions. Till here we have completed. So we'll move on to next part. So before going into that, so we need to do the ventilation calculation. So this is nothing but the fresh air inside the room. So every air conditioning equipment requires some fresh air. So if we are not providing some fresh air from the atmosphere, so the room air will be recirculated there itself, and it will be not healthy for the human beings. Okay, so first we will see how to calculate this. So for that we have to go to our data book, ventilation. Yes. So this I have taken from ASHRAE handbook. Okay, ASHRAE 62.1, ventilation for acceptable indoor air quality. So in this table we will have the different ventilation requirement for different applications. So for example, if it is office space, there will be different CFM, and if it is a university or computer lab, music theater, so based on the activity, so the CFM and the pressure requirement will be varied. Okay, so in this first we have the category. So our category is office space. So we will go to office space here. So here we have office space. Okay. So in this office space, first we required CFM per person. So per person, how much CFM is required? That is 5 CFM. And this nothing but the liter per second. CFM means cubic feet per minute. So cubic feet per minute, 1 cubic feet per minute, how much CFM is required? That is 5 CFM. So uh, if we say that if you take 1 cubic feet per minute, 1 cubic feet of area, so length, width into height, so that will become a cubic feet. So this 5 CFM is required for 1 cubic feet of area in a minute. Okay, so next one is a liter per second. So the CFM to liter per second is nothing but a conversion. So if somebody is working on units like inches, so they can take the liter per second and they can calculate. So here we have to use CFM per person. So this is the liter per second. And next is CFM for feet square. So CFM for square feet area. The floor area is 150 square feet. In our case, that is office space. So for 1 square feet, how much CFM is required? That is 0.06. So we need to multiply with 150. So then we will get the CFM. So that is CFM for feet square, and next is liter per second meter square. So that is 0.3. That is just a conversion. Okay. So first we will go to the data sheet, our sheet, and first we will have to enter the number of people. Okay. So if you see, the office space is 150 square feet. Okay. So maximum how many people they can sit? They can sit around 3 members or 4 members. They can sit. Okay. So if you assume that as a 3 members, so we can take here as a 3 members and we can calculate it. So the office space is very small, 150 square feet, so that I am considering that as a that will be used by 3 members. Okay. So in real time, so if the client gives the data, so we can take that. So otherwise we need to assume some value. Okay. So next, what is the CFM per person? CFM per person is office space, it is 5. Okay. So next I will enter uh, square feet. So before that I will multiply this. 5 into 3, it is 15. Next is square feet. How much square feet we are doing? That is 150 square feet. I will copy the same 150 square feet. This is the area of the room, nothing but. Okay. 150 square feet multiplied by CFM for square feet. And we need to take it from the data. So CFM for square feet is 0.06. You can see here CFM per square feet 0.06. So if you multiply this 150 multiplied by 0.06, will get 9. Okay, so we need to add this. So 15 plus 9, it will be 24. So 24 is our fresh air CFM. 24 CFM. Okay. So again we come to here and we need to write the outside air here. So infiltration, and this is the infiltration calculation. So infiltration nothing but the cracks present inside the doors, windows, and any other building cracks. So in generally nowadays, so the buildings are constructed in a tight way, and there will be not any openings or cracks present in the building. So that we can neglect this calculation. Okay. So outside air. So we need to find out the outside air heat. So when outside air is coming inside the room, so we need to calculate, we need to add some heat also. So that what we have to do, we need to take the CFM 24 and we'll keep it here. 24 CFM into degree Fahrenheit. This is nothing but our outside minus inside difference. Okay, so this nothing but the outside minus inside dry bulb temperature difference. So that is 35. So CFM multiplied by temperature multiplied by bypass factor. So we will discuss about this bypass factor. So what is bypass factor? It is the percentage of air which does not comes in contact with the coils. So if you remember that every air conditioning equipment, so when we send, it will take some air and it will comes with the, like, it will touch with the cooling coil. So what we are seeing in the image, so that is a cooling coil. It will touch and it will come inside the room. So then only it will be cooled. So but you cannot say that 100% of the air is touching the cooling coil and it is entering into the room. So some part of, like, 10% air will not be touched. So due to some gaps or something, so it will bypass it. So the air which is not touching the cooling coil and entering into the room, that we call it as a bypass air or bypass factor. Okay. So next one is contact factor. It is a percentage of air which comes in contact with the coil. So how much air is contacted with the coil, that is called contact factor. So the formula here is simple. Bypass factor plus contact factor equal to 1. Okay. So contact factor equal to 1 minus bypass factor. Okay, this is a very simple formula. Okay. So this is the bypass factor. So what we are taking now in this sheet is the bypass factor value. So to take the bypass factor value, we will refer one data. So coil bypass factor. Okay. So in table 14, typical bypass factors. So this is the uh, recommended bypass factors for the different applications. So we are doing for the application that the office spaces. So that office space comes under the comfort application, typical comfort application. So that will be not restricted to any other relative humidity maintenance. Nothing will not be there. So it is typical comfort application. So we can take the bypass factor value as 0.12. 0.20. Okay, so I will take 0.1 here. So we need to multiply this. So that is 24 multiplied by 35 multiplied 0.1 multiplied. There also 1.08 also there. We need to multiply it. 1.08. We get 90.72. We'll take 90 CFM, 90 BTU. Okay. So next is the internal heat. So how many people we have taken here? The people we have considered, that is 3 numbers. Okay. So we need to take the same here. People is internal heat, nothing but people is 3. And for individual people have some sensible and latent load. So for this we need to go to data again. So in this table only, table 12 we can get. So degree of activity. Degree of activity is office work. So they are doing office work. So we can select this. And application is offices, hotels, apartment, colleges. Any application we can select this value. If you come here, so we have more values like 1, 2, 3, 4, 5 values are there. So we need to select based on the room dry bulb temperature. So we'll go to our data sheet. So what is the room dry bulb? Room dry bulb is 75 degree Fahrenheit. So we'll go there. So here if you see, this is the 75 degree Fahrenheit. So in office space, this is office space, 75 degree Fahrenheit means this is our values. We have two values. So we are doing for the sensible valley heat. So that is 245. Okay. So I will write 245 here. Okay. So if you multiply 245 by 3, multiplied by 3, 735 will get. Okay. Next is nothing but the power, power nothing but any other power generating equipments. If we have, we can take that, otherwise we can leave it. So here we will leave that. And next is lighting load. So if you see, lights will also emit some heat. So if you uh, if you touch the light, so it will be very hot, or otherwise if you sit exactly on the bottom of the light, so we will get very heat. So that heat also will is important for our calculation. So we need to take that heat. So here what we'll take, we will consider 1 watt per square feet as a thumb rule calculation for lighting load. So if you don't know the exact lighting source taken in the calculation, so if the electrical calculation is done before this and we get the exact values, so we can take that. Otherwise we can take the 1 watt per square feet. So if we take 1 watt per square feet, what is the square feet here? 150 square feet. So it will be 150 watts. 150 watts. So when you multiply 150 watts with 3.4, it is 510 BTU. Okay. So next one is very important load. So that will affect all the heat load calculation results. So that is nothing but the equipment load. Here it was written as appliances. So nothing but the equipment load. Equipment load nothing but when you are sorry, for example, if you take this office space only, so people will be using the laptops, systems, printers, so all other electrical equipment. So if people was using these kind of equipment, so that will emit some heat inside the room. So that plays a major role in calculating heat load. So that we need to consider in every room. So not only for the office space, if you take for example in our home, so if you are designing for the living room, so there will be one uh, TV and like refrigerators will be there. So different types of equipment. So you go for any manufacturing industry, for food manufacturing industry like that, so there will be large machineries will be there. It will emits more heat to the room. So there it is a major issue that we need to find out the heat load, that kilowatt, and we need to add in our these things. So here, okay, so whenever we are designing any room, any air conditioning equipment, so the equipment load is very important. So that we need to consider. So here, in our this is our office area, which is very small. So we are considered three members. So if you take the three members was using three systems, so one system will approximately it is of zero point 0.2 kilowatt or 200 watts. So 200 into 3, it is 600 watts plus around one printer if they are using. So the printer is also has 200 watts. So it will be around 800 watts. So I'll take this 800 watts. Okay. So when we multiply this 800 by multiplied by 3.4, 2720. Okay. So this is the equipment load electrical. So next one is room sensible heat. So room sensible heat, we need to add all this. Okay. So if we add all this and the total room sensible heat, we will get it here. So I will add this 420 plus 3280 plus 2031 plus 1354 plus 384 plus 1174 plus 2700 plus 1530 plus 90 plus 510 plus 2720 plus 2720. So we'll get 16,193 BTU. So I'll write it here. So this is the BTU. So here we need to, sorry, this I need to place it here. Okay. So this section nothing but the supply heat gain. So when you are sending the air through the ducts or there will be any leakages or fan safety. So everything, if you consider some safety factor, we need to take it. So that I will consider that as a 5% safety. So this is the entire sensible heat, that is 16,193. So if I consider some safety factor of 5%, so I will multiply this with 0.05. So that is 809. So this is the safety factor, 809. Okay. So when we add both these both, we will get the final AFM 809 plus 16193. We will get is 17,000. This is our final effective room sensible heat. Okay. So after this, we need to enter the room latent heat. So infiltration CFM is not there. We are not considering. There is no cracks in the building. So we are not taking this. The next one is outside air CFM. So this here also we have taken the outside air CFM. This is sensible heat and this is the latent heat. So outside air heat is CFM is same, that is 24. Okay, this is the 24 CFM. And next one is grains per LB. So humidity ratio. So difference humidity ratio, how much we got here. This is the grains per LB humidity ratio. That is 75 minus 65 is 10. To take this, we will place it here. So bypass factor we have already taken. What is the bypass factor here? 0.1. I'll place it here. So when we multiply this, we can get the value. 24 multiplied by 10, 0.1 is 24 CFM into this we need to 0.68. So it is 16.32. So I'll write it as 16. Okay. Next same here also we have taken the people load. So next here in latent load also we need to take. So number of people is same, that is 3. And we need to go for the data book. So this is the value we have taken. There is 75 degree Fahrenheit dry bulb temperature, room dry bulb temperature, and this is the office work. So we got two values, one is sensible and one is latent. Sensible we have already taken, so now we are taking latent heat, that is 205. So 205 multiplied by 3, 615. Okay, so rest of the things is not required any steam generating, so steam is not required in our office areas. So in pharmaceutical somewhere they will use, and appliances vapor transmission also will not be there. So we need to add the total latent heat. So what will be the latent heat? So it will be 615 plus 16, that is also almost 631. 631. So again we will add some safety factor in latent heat also. So that is 631 multiplied by 5% we are taking, that is 31. Okay, so finally if we add these two, so it is 662. Okay, so next is outside air heat. So outside air heat we need to calculate. One is sensible and one is latent heat. So very simple. CFM, outside air CFM we got already, that is 24. We need to take it here. 24 here, and also this is also 24. Okay, so next one is temperature, dry bulb temperature. How much that is? 35 here. So I will write it here 35, and 1 minus bypass factor. 1 minus bypass factor we need to do it here. So what is the bypass factor here? It is 0.1. Okay, 1 minus 0.1. How much we'll get? We'll get 0.9. Okay, so I will write it 0.9 here. Okay, again 0.9 here. So if you multiply this, we'll get the BTU. So 24 multiplied by 35 is the dry bulb room difference, into 1 minus bypass factor we have done, that is 0.9 value, into 1.08. How much we got? We got 816. Okay, next one is same 24 CFM multiplied by, here it is grains per LB. Grains per LB is the difference, my humidity ratio inside minus outdoor. Outside, what that is 10. We have already taken, so that we need to take it here. So this is the difference we have taken from the inside minus outside conditions. This is a 10 humidity ratio difference. Okay, so 24 multiplied by 10 multiplied by our 1 minus bypass factor, it is 0.9 multiplied by 0.68, it is 146. Okay, so we need to add all the grand total heat, and also if you required you can add some safety factor, but not required, so we have already taken. So this is the grand to heat subtotal. So we need to add all the heats here. So that is nothing but the effective room sensible heat, latent heat, and these two loads. So I will add this. 17,000 is our sensible heat, plus 662 is our latent heat, plus this is the two values of outside air heat, plus 816 plus 146. This 18,624. Okay, so we got finally the total heat. So to get the tonnage, so we need to divide it by 12,000. 1 TR equal 12,000 BTU. So that's why I'm dividing it by 12,000. So how much tonnage we got here? That is 1.5 TR. So I'll write the formula here. So total BTU divided by 12,000, we will get tonnage. So when we discussed before the heat load calculation, that by you doing the calculation, we will get the two values. One is tonnage and one is CFM. So we got the tonnage by doing all these methods. Okay, so next we need to find out the CFM. So CFM we can find out from the rest of the calculations. We will see. Okay, so that's also very simple. We will complete it today. So effective room sensible heat divided by effective room total heat. What is the effective room sensible heat? So this is our effective room sensible heat. It is 17,000. So 17,000 divided by total heat. What is the total heat? Total heat we need to take without adding these 869 and 146 values. Okay. So I will add this total heat, that is 17,000 plus 662. We'll get 17,662. Okay. Remember that we don't take the total heat value including this outside area heat. So we need to take without this outside area heat. So that is 17,662. So when we do this, we'll get the sensible heat factor. So we'll multiply 17,000 divided by 17,662. We'll get 0.96. It is the sensible heat factor. Nine six is the sensible heat factor. So next we need to find out the indicated ADP and selected. Selected ADP will not be required. It is depend upon the unit selections. If you selected the ductable unit, chilled water coil, so it will depend on that. So usually we will take the indicated selected indicated ADP here. Okay. So for this ADP, sorry, we need to select this selected ADP. So we'll go for the, we have to go for the different uh, data book ADP, where it is, this is selected ADP. So to select the ADP, we required a room conditions of dry bulb, RH and wet bulb and humidity ratio. So we know that room dry bulb conditions and RH conditions. So what is the room dry bulb condition? It is 75 and RH is 50. So I will select that. So room dry bulb is 75. So here it is 85, 81. So it is very high. I will go to 75. So this is the room dry bulb 75. So we can select in this chart. And after that we need to go for the relative humidity. This is the 75 and the relative humidity is 50. So this is our relative humidity 50%. So 75 and 50. So we can select these values. But here also if you see we have more number of values. So for this we need to take the ESHF, effective room sensible heat factor. So that we calculated how much we got here, that is 0.96. So 75, 50 and 0.96. So where it is 0.96. we have 0.92 and 1. So it is nearby 92. So we can take the value as 54. Okay. So we'll write this 54 here. Yes, 54. So next one is 1 minus bypass factor. We have already done 1 minus bypass factor here. So the value is 0.9. So I'll copy this. So I will place it here. 1 minus bypass factor 0.9. Room temperature minus ADP. So what is the room temperature here? 75. 75 minus 54. 75 minus 54. 54 is nothing but ADP. We'll get 21 here. Sorry, 21. So when we multiply this 0.9 into 21, we will get dehumidified rice, that is 18.9. So 18.9 is dehumidified rice. Okay, so next is the final formula to calculate the sensible heat. So what is the room sensible heat? We know that it is 17,000 divided by 1.08 into dehumidified rice. Dehumidified rice is, we have calculated, that is 18.9. Okay, 1.08 multiplied by 18.9. So we'll get 20.412. 20.412. So if we do this, 17,000 divided by 20.41, we will get 832 CFM. This is the final CFM we will get, that is 832. So finally we have completed the heat load calculation. So by this we got the value of CFM, that is 832. I will keep it here, and tonnage I will keep it here. So 1.5 TR and T2 CFM. So based on that, when you are selecting the equipment, so if you are purchasing any air conditioning equipment, you can say that 1.5 TR tonnage and 832 CFM air is required for the air conditioning system. So based on that, you can select the unit. Okay. So till here, if anyone has doubts, you can ask me. Okay, so practice it, whatever the assignment I have given. So complete this in manually method. So don't worry. So this is a manual method. So it is looks like very hard, bit hard. So but when we are doing it in Excel sheet. So tomorrow I will say you the Excel sheet. So it we can complete in with just 5 minutes. Okay. So the same procedure what we have done for 3 days, we can complete it in 3 days. Sorry, the in a 5 minutes. Okay. So no need to worry, but this is for your understanding in a manual method. So every formula will be under. So today we'll see the Excel method for calculating the heat load. So the same method, so it will save a lot of time by doing in Excel. So we'll enter the values and the same values what we have taken in the manual calculation, and we will compare the results the both. Okay, so how to use this Excel sheet? So you can see here, so these yellow color values will be calculated automatically, so no need to enter anything on the yellow cells. So the only the white color cells we need to enter it manually. Okay, so starting here we have the conditions outside and inside. So we will enter from the manual sheet. Okay, so first what is the outside conditions? So that is 110 degrees dry bulb, it's already there, and 75 wet bulb, 20% RH, and so 20% RH, and humidity ratio 75, and dew point temperature is 59. Okay, so it was already entered. So I am leaving like that samely. So inside conditions, room dry bulb is 75 degrees and wet bulb is 63, and RH is 50, and humidity ratio is 65, and dew point temperature is 55. Okay, so the difference will be calculated automatically here. Okay, so next we need to enter the area. So the area is 150 square feet. Okay, so here we have taken. So the same we need to enter 150 square feet. So the height, so that is a true ceiling height. It's not required. We will keep it as blank. And false ceiling height that we assumed as a 9 feet. So I will keep it as a 9 feet here. So the volume will be calculated automatically. So again, after this we need to calculate the fresh air requirement. So here we have done the fresh air requirement. So this is the part. So here we need to enter the number of people inside the room. Okay, that we have entered 3. Okay, so next CFM per person, that is 5. We have taken yesterday from the data book. So the same we need to enter, and CFM per square feet it is 0.06. Okay, so the total fresh air requirement will be added here, that is 24. And next we need to come for the solar heat gain through glasses. So this is the part. South and west side we have the glasses. So this is the south side and this is the west side. So first one is here, it is temperature. So what is the temperature we have taken? So south side it is 12 and west side it is 164, right? And the factor nothing but U value, that is 1 and 1, right? And area west side is 20 and south side is 35. So the BTU it will be calculated automatically. So next wall side, south wall and west wall. So west wall is 43 and south wall also 43. That is the temperature difference. Okay. And next one U value is 0.35, same. Area is 90 and 135. Yes, correct. 90 for west side and south is 135. So next we go for the roof. Roof 150 square feet. This 150 square feet will be taken automatically. We have to enter only the roof temperature difference and U factor. So the temperature difference is 32 and U value is 0.08. Okay. So next is all glasses transmission. All glasses transmission, only here we need to enter the U values. So the rest of the values will be taken automatically. So the all glasses U value is 0.61 here. And ceiling we are not take ceiling we have not taken anything. The partition next. Floor we have taken. The U value is 0.34. Is the same. We can leave it. And partition glass. Partition glass U value is 0.40. That is right. Okay. And this 225. So this is the partition wall area. So this is the partition wall area 225. Yes, same. Okay. And next infiltration and outside air. Infiltration we have not considered anything. The outside air will be calculated automatically. Only the internal heat we need to enter. What is the internal heat? First one is people. People BTU we need to enter. So that is 245. 245. So the number of people and BTU will be calculated. Only we need to enter per person BTU. Next is lights wattage. So light wattage is 150. 1 watt for square feet we have taken. So that the value will be 150. And next one is equipment watt. Equipment wattage is 800 watts we have taken. The same we can enter here. So remaining everything will be calculated. And next is latent heat BTU. This is nothing but the room latent heat. This is the value 205. The same is already there. So that's it. Everything will be calculated automatically. So the tonnage, everything. Only we need to enter the dew point temperature here. So we got the dew point temperature. How much? ADP value. Selected ADP is 54. So the same was there. 54 here. Okay. So finally the values you can see here. That is CFM we got here. It is 832 and here we got 871. So slightly variation will be there from Excel to manual. This is the 871 CFM and tonnage here it is 1.62 TR. Here it is 1.5 TR. So this is how we will calculate with the help of Excel sheet. So in Excel sheet, this is the advantage. So every time we don't need to enter the all the values. So the only the U values and area values we need to enter. Okay. So if anybody has doubt in this Excel sheet, you can ask me.